Hi, everyone. We would like to welcome you all to this talk of the IEEE GRSS-APS student chapter at UST. Today, we are pleased and honored to have this talk presented by Professor Sien Ham, entitled Advanced Electromagnetic Surfaces, Intelligent Design Methods and Implementation. Professor Sien Victor Ham received the BS, MS, and PhD degrees in Electrical and Computer Engineering from the University of Calgary, Canada, in 1999, 2001, and 2006, respectively. In 2006, he joined the Edward S. Rogers Senior Department of Electrical and Computer Engineering at the University of Toronto, Canada, where he's currently a professor and the Eugene V. Polistock Chair in Electromagnetic Design. He leads the Reconfigurable Antenna Laboratory and, along with his students, conducts research in the areas of advanced electromagnetic surfaces, reconfigurable multifunction antennas, space-fed arrays, and antennas for space applications. Dr. Ham was a recipient of the Governor General's Gold Medal in 2001, the IEEE Antennas and Propagation Society Student Paper Award in 2004, the AS Tech Leaders of Tomorrow Award in 2006, the Early Researcher Award from the Government of Ontario in 2012. On the teaching side, he has been the recipient of Departmental Teaching Awards and a Faculty Early Career Teaching Award. He was a co-recipient of the IEEE Antennas and Propagation Society RWP King Award in 2015 and 2017. He served as an associate editor for the IEEE Transactions on Antennas and Propagation from 2010 to 2017, and he's currently co-chair of the IEEE APS Education Committee. Now we should start, but before that, kindly put your microphone on mute and also send your questions in the chat box, which will be addressed at the end of the talk. Professor Ham, the floor is yours.
Okay, thank you very much, Michelle, and thank you, Kazem, as well, for inviting me to speak today. It's a true honor to be here in LA with you to give this talk, and it's wonderful that we can just transport ourselves and give these talks like that these days. So thank you all for coming. So I hope you find the talk interesting. As Michelle said, my name is Sean Hum, and we're going to be talking principally about electromagnetic surfaces today, but I want to focus on design methods for those surfaces and some interesting implementations that we've carried out based on those design methods. So let me begin just by introducing myself a little bit here. So as Michelle mentioned, I'm from the University of Calgary originally. And while I was in grad school, I was working with TR Labs, which is a nonprofit research, telecom research consortium in Western Canada at the time. And I joined the UoT in 2006. And I've also spent some time overseas working with ESA Tech in Noorwegen, the Netherlands, and also Universidad Politécnica de Madrid. Back in 2015. So I moved from Calgary, which is not too far from this beautiful mountain lake that you see here, Lake O'Hara, one of my favorite hikes in the Continental Divide, separating in the Canadian Rockies, separating Alberta and British Columbia. And now I reside close to this other lake, Lake Ontario, one of the Great Lakes in this region. I'm from the University of Toronto now. Just to tell you a little bit about UoT, you can see a nice aerial shot of the downtown campus in this photo. We have almost 100,000 students in Toronto, so it's really like a small village in itself. 20,000 of those students are graduate students, and there's about 15,000 faculty members. We receive about almost $1.5 billion annually in research funding, and generally ranked top in Canada, about number 5 in North America, and this year number 18 worldwide, depending on who you look, which sources you look at. Within our own department, we have about 88 faculty, 1,000 undergraduate students, about half as many graduate students. Okay, so our talk today is going to be about what I term advanced electromagnetic surfaces. This is a catch-all term that I use to cover a spectrum of surfaces that you see in the picture here. So these encompass reflect arrays and transit arrays, which are spatially fed antenna arrays, frequency selective surfaces, and polarizers. So those are relatively old surfaces that have been around for a long time. But as we move towards the right-hand side of the diagram, we move towards impedance surfaces, which are maybe a bit newer, and then meta surfaces and metagratings, which is really a topic of a lot of research these days. And they all share the same thing in common, as in that they allow for very exotic manipulation of an electromagnetic wave. It's just a matter of what they're doing. So reflector arrays and transmit arrays are generally designed as beamformers. Frequency selective surfaces are designed to obviously manipulate the frequency content of a wave. Polarizers, the polarization of a wave. And then these meta surfaces, metagratings, and impedance surfaces are really targeting changing the modal composition of if it's a periodic incident wave, changing the modes there, or realizing some sort of complex aperture distribution in general, which is very useful for antenna applications, whether it's in the microwave, millimeter wave, or photonic regime. And I'd point out that all these pictures look like they're passive surfaces, but we can make active surfaces, reconfigurable surfaces, and many of you may have heard of these space-time surfaces where you have temporal modulation of reactances in the surface to do interesting things like realize non-reciprocal behavior. So here are just a few examples of different advanced electromagnetic surfaces you can find out in the wild all around the world. I won't talk about all of these different implementations, but you can see that they share physical features in common. They're very thin, flat, and generally used in conjunction with antennas, at least when operating in the microwave regime. So our talk today is going to be focused on the design process around these AESs. And this design process is composed of three main steps. So the first step, which we see over here, is defining the wave transformation that you want the surface to do. And maybe we're transforming fields E1 and H1 into fields E2 and H2. E2 and H2 might be on the same side of the surface as E1 and H1, like a reflecting mode surface, or it could be on the other side and it's a transmitting mode surface. It doesn't really matter. And what we need to do is define some sort of surface properties or macroscopic electromagnetic properties of the surface that it needs to realize to make this transformation possible. And so that's sort of a mathematical definition of what the surface is going to do. And then you need to translate that after step 2 into a physical unit cell composed of dielectrics and conductors that actually carries that out. And then, of course, the last step is to prototype it. So the talk today is really going to talk about all of these steps. And that's roughly how I've organized the presentation. We'll start with the macroscopic step, which uses optimization methods to accomplish that. And then I'll talk about two different unique design methods for the microscopic step, one using equivalent circuit models, which are nice and easy to understand and build a physical intuition around how these surfaces work. And then a more advanced topic using a data analytic approach based on machine learning. And at the end, I'll show you some experimental realizations of these surfaces. So let's begin with the first step, which is the macroscopic step. So this really concerns the design of the AES's surface parameters. And we can use a variety of parameters to define an AES. For example, we can use surface impedance, surface admittance, and electromagnetic coupling coefficient if we have an isotropy to define a surface. We could use susceptibilities, both electric and magnetic susceptibilities to define the surface. We could use polarizabilities. We can even use S parameters or other network parameters to define how a surface works. And all of these parameters are functions of position. As we walk around the surface, they spatially vary to accomplish some sort of transformation of the field. They could be uniform in the case of something like an FSS, but generally they vary as a function of the atomic position. And I'd point out that all of these surface parameter descriptions are interchangeable. So some people like to use susceptibilities, some people prefer to use surface impedances. You can convert from one to another. In fact, in the old days, sometimes we just defined things in terms of like the phase gradient that we want to realize from the surface. But nowadays, we tend to focus more on these mathematical descriptors of the surface. And we define the transformation in terms of the desired tangential fields existing at the surface of these AESs. So that allows us to write equations such as this. These are the generalized sheet transition conditions in black, which allow us to relate the average field at the location of the surface to the fields on either side, knowing the surface impedance tensor Z sub SE and the surface admittance tensor Y sub SM. And if we have bi-anisotropy, then we would add these blue terms here where there's a coupling between the electric and magnetic response of the surface. And it's really these extra terms here that allow us to do some really amazing things with these surfaces now, because we can make them power conserving, or we can do power conserving transformations. So as antenna engineers, we are actually not so concerned about strictly specifying E1 and E2, H1 and H2. We might know what E1 and H1 are, and because we're illuminating the surface with something, but we might not necessarily know E2 and H2. In fact, we're more concerned with constraining those fields than actually specifically prescribing them. For example, if we want to get a radiation pattern, let's say we want a specific radiation pattern from the surface, well, radiation patterns are usually phaseless, right? We don't usually specify how the phase varies across the surface. So we actually don't have complete information on the far zone fields anyway. But more often, especially in shaped beam applications, we will define an upper and lower mask that the radiation pattern from the antenna is supposed to lie between. And so we're not being very specific in terms of the exact fields that we want. We just know that we want the radiation pattern to comply with the mask. We also might specify that we want nulls in the radiation pattern, but the field can do what it wants elsewhere. So these are all constraints and not specific stipulations on the field. So without knowledge of the exact tangential fields at the surface, and we can't go and solve these equations for the surface parameters, right? Because we actually don't know E2 and H2. So, and even if we did know E2 and H2, it can still be complicated because you have mutual coupling between the elements in the surface. And if that mutual coupling is significant, then one element can affect the response somewhere else on the surface. And then the surface is what we call a non-local response. And then that complicates the design. So the macroscopic design step is designed to try to address this. At the microscopic level, this is really where the black art or black magic around designing electromagnetic surfaces comes in. You can see these many weird and wonderful ways of inventing the atoms in these meta surfaces. And generally their design requires tedious analysis and full wave simulation package. You adjust some parameter or some configuration of the scatter, and then you run the simulation again, and you see if you've achieved the surface parameters that you're looking for. So ultimately, as a designer, our goal is really to do the opposite, right? We would like to specify what the surface parameters are and have a tool that spits out what are the geometrical dimensions of the scatter, right? And that's called an inverse design problem. And we're going to be looking at that in a bit more detail later. Before we get into that, I'll talk about the macroscopic design step. And to accomplish this, we've been using optimization methods that are inspired by convex optimization, but that we've had to relax using Lagrangian methods. So as I said before, the usual process is if you know the field transformation that you want to accomplish with the surface, then it's easy. You know the tangential fields, and on both sides of the surface, you can determine the appropriate surface parameters that the surface needs to realize. And in this talk, I'm going to focus on this impedance and this surface impedance, surface admittance, and electromagnetic coupling coefficient tensors to describe the surface. So knowing the fields, we can then solve for the electric and magnetic currents on the surface, and then solve for these surface parameters. And this has been done before by others. So what we want to do is get away from that and actually just constrain what the fields E2 and H2 are going to be. And we talked about what some of those constraints look like already. We might specify the beam width or side lobe level or null location, something less specific than specifying the field itself. But now we don't know the tangential fields. We only have these far zone constraints. And so now we've got a problem in trying to determine these surface parameters. So there have been some approaches in the past to try to circumvent this problem. In the field of reflect rays, there are these phase-only synthesis procedures that are based on intersection methods that try to solve for the reflect ray elements as a function of position that you need to realize a specific phase or a radiation mask. Our approach is a little different. We want to try to modernize this and bring techniques such as that into the world of metasurfaces, where we actually have control over 3 sets of parameters, not just the phase, Z, SE, YSM, and KEM. And our approach is to try to use convex optimization to determine these surface parameters from far field criteria. I say attempt because we can't actually use a convex method directly. So let's start with a system description, and we'll just do this in 2 dimensions to make it a bit easier. So here's our AES lying along the y-axis, and we'll subject it to some incident field, and there'll be a reflected field generated and a refracted field, and they might be plane waves, they might not, but this is just a general diagram. And we have the electric field integral equation here relating the constraining basically the electric field at the location of the surface, or the tangential fields at the location of the surface. So we know that the sum of the incident and the scattered field has to be equal to this sum of products here, where again, we see the surface parameters, 2 sets of the surface parameters entering into the electric field integral equation. So we may have electric surface current densities as well as magnetic surface current densities on the surface. So the scattered field we can compute knowing the electric surface current density, and we just use a 2D Green's function to compute that here. And what we'll do is we'll break these currents, these surface currents, J sub Z and M sub Y in this 2D example, and we'll express them as a superposition of basis functions, because our goal is to try to form a linear system of equations a la the method of moments to form a 2D description of our system. So we'll break down the electric surface current density into a series of basis functions. We'll use the same basis functions for the magnetic surface current density. And then we need to have a look at what's going on with the magnetic fields next. So the magnetic field is the scattered magnetic field has obviously a different equation that depends on the magnetic surface current density here. And we can then test these equations at every point along the region of our AES. And we do point matching basically to try to solve for our unknowns. So we form a linear system of equations here relating the incident field and the currents on the surface as well as the surface parameters. Okay, and this is a nice linear system that we can then try to use in our optimization problem. So this looks like a lot like a classic method of moments implementation of a surface, except that the surface has got surface parameters to it. It's not a conducting surface or a perfectly conducting surface. So we have these impedance matrices and admittance matrices that allow us to relate everything, and they're described with these equations here. So with this complete system, what's nice is that if I step back here, we can actually say that the surface impedance, ZSE, the surface admittance, YSM, we can say that these are lossless. We would like our AES to nominally be loss-free, right? So we can make these purely imaginary matrices. And we can also make this electromagnetic coupling coefficient matrix purely real in an effort to try to realize a lossless passive AES. So what's nice about forming the system this way is that by construction, we can make our system passive and lossless. And this is different from what others do in the literature, where they try to solve for the surface parameters, and then they end up with significant real parts, for example, the surface impedance, that may be positive or negative, which leads to this active lossy behavior that we classically see in early metasurfaces that then needs to be handled somehow. So our system forces essentially systems to our solution to avoid active lossy behavior. Now we need to constrain the far zone field. So we need to relate the surface currents to the far zone E field. So we'll just use a G matrix to do that. And these are just, again, just simple matrices that transform the currents on the surface to the far zone fields. Okay, so now let's turn to our attention to the optimization problem. So we want to solve an optimization problem that looks like this. So we have some cost function, which I haven't defined yet, but the cost function depends on the surface current, the electric and magnetic surface currents on the surface, as well as the surface parameters, and we're trying to optimize all of these, subject to the GSTCs, right? These are basically the matrix form of the GSTCs, a discrete form of the GSTCs as I showed earlier. So we're trying to satisfy the GSTCs on the surface. And then we might throw in some additional constraints, which I'll talk about later. So this is our fundamental optimization problem, and it's looking good so far. We would like to try to solve for all of these unknown parameters. But the problem is that this the constraints, the GSTCs here, are actually non-convex because we have some bilinear terms here. We're actually multiplying two of our unknown quantities together, right? So this is called a bilinear variable. So this makes the problem non-convex, and we need to try to find a way to solve this optimization problem by some other way. So what we do is we relax it, and a relaxation is a way to solve a non-convex problem by enlarging the solution space. And we use a special technique called the alternating direction method of multipliers, ADMM, that forms a dual problem, an augmented Lagrangian, and alternatingly minimizes it with respect to one set of the bilinear variables at each iteration. So if we return to our problem here, this is the one that we showed earlier. The so-called dual problem of this is minimizing this Lagrangian here. And if you solve the dual problem, you solve the primal problem. And so here's a dual problem where we're trying to solve for just the currents in this optimization problem. Okay, and then it's called an augmented Lagrangian because we actually add these penalty terms here to improve the convergence of the optimizer. So that's what makes it ADMM. And so in this step, we solve for the surface currents, but then in the next iteration, we'll try to solve for these surface parameters, and then we just alternate back and forth. And that's why it's called ADMM. So this is a big, ugly flowchart of what the algorithm actually looks like. So this is one iteration solving for the currents, and then the next iteration solving for the other sets of variables, the surface parameters, updating the problem, checking for convergence, and then looping back and repeating until this optimization problem hopefully converges on a solution. So we need to define this cost function now, F naught. And this is where we put our antenna hats on, right? So what sort of things might we want to do? We might, for example, want to form a beam in a certain direction. So what we can do is we could say, okay, let's form a beam in this direction with some certain amplitude. And if you look at the first three terms in this expression, this is just a total field produced by the surface. So if we subtract the desired electric field level from this, then our goal would be to minimize this norm, right, in the direction phi naught, and that should produce the beam that we want. Null forming is even easier to understand. We just want to take the total field here and make it zero, right, at some angle phi n. So this is an easy cost function to understand. Another very common one is enforcing a maximum permissible side lobe level. We can call it tau. And again, we could just take the total field in some side lobe region and say, okay, we're not allowed to exceed tau in this interval. And sometimes we throw in a slack variable here to make it a little bit easier to optimize. So these are examples of constraints and cost functions that we can introduce in the problem to make it to solve a specific antenna problem. And we can also even make the surface currents smooth by adding a cost function for that, just to make sure that the surface is realizable in the end. Because if we have sharply varying currents, that's probably going to lead to sharply varying surface parameters, which are hard to realize. So here's an example of a multi-criteria optimization problem that we threw at this optimizer. We said, okay, let's take a 15 wavelength surface and ask it to take an incident plane wave and divert it in 3 different directions, which you see given in the table here. The main beam level was specified, and then we also constrained the side lobe level to not exceed the green lines that you see in the figure. We specified some null angles, which you can't see in this polar plot because they're at the center, and then we put a curvature constraint on the current, excuse me. And this is the pattern that the optimizer came up with along with the surface parameters, which I haven't plotted here. So now we know the surface parameters is a function of position as we walk along the AES, and if we illuminate it with a plane wave at normal incidence, it will produce this interesting pattern. Here's another example. This is an example of an extreme refraction metasurface. So it's designed to take an incident plane wave and refract it at a very extreme angle, 72 degrees, from the normal axis. And that might not sound like a big deal, but 72 degrees is quite large, and this surface is very small. It's only 3 wavelengths long. And the reason we chose this specific example is because edge effects become very prominent in such an electrically short surface. So mutual coupling between all of the elements is is now a big deal. And classic methods don't deal with the mutual coupling between atoms in the design, but the optimizer, that's built into the optimizer. So it should be able to correct for the mutual coupling on its own. And we actually see that in the figure. If we take this refraction example as a perfect analytic example, we can actually analytically compute what the surface parameters need to be on the surface to refract the normally incident plane wave to 72 degrees. But if we plug that into the surface, it actually does a pretty poor job, as you can see in red, because of all the mutual coupling that was not accounted for in the analytical solution. But then we see that when we run it through the optimizer, we produce the beam in the correct direction, and the pattern is much, much nicer. All right, so just some remarks to close out this part on the macroscopic design process is that I think it's a very useful and flexible framework that allows designers to use these AESs in a very practical way without having to have any prior knowledge of the radiated fields. One thing we are trying to add is to introduce minimum field constraints to the proposed framework, because when I showed you those radiation masks earlier, there was an upper mask and a lower mask, and the radiation needs to be between them. We haven't implemented the min field constraint yet. So what I'm going to talk about next is merging this macroscopic design step with the microscopic design step. So that's step 2 of our 3-part process, right? So let's move on to the next part of the talk. So I mentioned that I would talk about 2 different ways to approach the design of the atoms in the AES. And the very first technique that I'll show is one based on equivalent circuit modeling. I like this method because as designers, we really ought to know what's going on with these atoms that we're designing, right? And I think equivalent circuit models are a very useful tool in helping us understand how to design these atoms. But at the same time, they have this great advantage that equivalent circuits are very fast to evaluate, right? Circuit simulators are very, very fast compared to EM simulation tools. So if we can come up with an equivalent circuit model for this unit cell and predict the generalized scattering matrix of it from a circuit model, this would be way faster than trying to run a full wave simulation in HFSS or CST or whatever tools you might use. And maybe it's not as accurate as a full wave tool, but our goal is to try to provide rapid first order projections of the response of the cell that helps the designer get started. And then if you want to refine things later with a full wave tool, then you can do that. So our starting point for the equivalent circuit model is actually going to be this simple dipole problem. This is a driven dipole in a periodic array. So this is like a phased array, a dipole that it could be printed on a substrate or not. That doesn't really matter here. But it's in a periodic environment. And I chose a dipole because the current distribution is principally X polarized, okay? So that we don't have to worry about the other components of the current density quite yet. So let's say that the X component of the current distribution is this function F, and it might vary as a function of X and Y over the dipole. And let's say that F has a Fourier transform F tilde. Then we can express the current distribution on our dipole as a Floquet series, right? Because of the periodic nature of the problem that we're solving. Now let's assume that F is separable so that the variation of the current distribution on our dipole has a function describing how it varies with X, which we'll call G, and it has a function that varies that describes how the current will vary with Y, which we'll call H. And this is a textbook problem that's discussed in this book here of deriving what is the input impedance seen looking into this dipole here. So this is the active input impedance. And the expression looks like this. And you basically, what's nice is it's a completely an analytical expression, knowing the Fourier transform of the current distribution on the dipole. And generally, we know what that current distribution looks like, so we can compute its Fourier transform. Well, then we can actually analytically predict the input impedance. And I'll describe what some of these terms in this equation are. So these capital G and H are the Fourier transforms of little g and little h evaluated at the Floquet wave numbers. And then these terms in the denominator, y sub mn, te, and tm, these are admittances or normalized wave admittances. And what they are is that if we imagine standing on the surface, like at the surface of the dipole, what wave admittance do we see at that point? Well, we see a wave admittance looking upward, right? Because above this dipole is free space. And we see a wave admittance looking downward, which in this problem, there's a substrate here and it's grounded. So we see a grounded dielectric substrate. And so the circuit looks like this, right? Looking down, we see this transmission line that's been shorted out. Looking up, we see an infinite transmission line. And these transmission lines have modal impedances associated with them, right? But we'll express it here in terms of admittances. So we just basically put these two in parallel with each other. And that's what these expressions represent in the denominator. So the reason these expressions in the denominator are so important is that I can take this expression for ZFL here. I'm going to simplify it, okay? So we're going to write it like we see up here and just leave the terms in the denominator and then collect everything else into these terms that you see here, T super TE and T super TM. Okay, and then you can see how I've, what's balled up in TTE and TTM here. But what's useful about this form of the input impedance is that it suggests an equivalent circuit that you see here. Because what are we doing? We're taking a bunch of impedances and we're adding them all together. So it's a series combination of impedances. But we're doing more than that. We're taking this impedance, this 1 over Y, and then we're multiplying it by a term. That reminds us of a transformer, right? We're taking a transformer, and then if the transformer turns ratio is root n, then we scale the impedance by n, right? So these transformer turns ratios, these T's, appear and take that modal admittance that I described to you on the previous page, where you have a short-circuited transmission line here and an infinite line here in parallel. And then we have to transform that before it can be seen by ZFL here, right? So this is the basis of the equivalent circuit moving forward. But this is for a driven problem, right? We're driving this dipole and we're seeing what is the active input impedance or active reflection coefficient seen looking into this, which is a very useful problem for phased arrays. But in AESs, we don't usually drive them like this. We usually illuminate them from above or below. So we can modify this equivalent circuit to analyze not this driven dipole problem. So we'll take away these terminals and maybe we replace that with a load, but now we can illuminate this dipole from the Fouquet port. And then we're interested in what is the reflection coefficient seen at the Fouquet port, or what is the transmission coefficient if this was a transmitting surface on the other side here. And that allows us to form the generalized scattering matrix of this periodic structure. So all we have to do is we're not driving this dipole anymore. In fact, we could put a load here or not, but we'll just keep it general and put a load impedance, maybe even a reconfigurable one. And what we'll do is we'll look into one of these ports here, like we were looking into this infinite transmission line. Well, now we're illuminating from one of those transmission lines. We're illuminating with a specific mode, maybe the TE00 mode. And we'll look at what that Fouquet port sees. And that could be the input impedance, which allows us to compute input reflection coefficient, which is the S11 for the TE00 mode. So this turns out to work quite well. We initially used it for reconfigurable reflector array elements, these patch-like elements that you see here, where we put a varactor diode to implement a variable capacitance across this gap region. Here it's a distributed capacitance just for simplicity, but you can see some dimensions of a patch here. And as we vary this load capacitance that's placed across this region, you can see that the equivalent circuit model aligns very, very well with a full wave method of moment simulation that takes much longer to run. And you can get the so-called S-curve for the reflector array element in this way. So that's really great for reflector array designers, right? You have an analytical expression for the S-curve that you don't need to run any simulations for. And even if it wasn't a reconfigurable element, let's say it was just a fixed patch reflector array, just square patches, no loads. Well, then I can just set this load to be a short circuit, right? And just connect the two halves of the patch together and vary the size of the patch. And so here's an example of just a square patch, a variable patch size reflector array. And again, we can get the S-curve for even a non-reconfigurable reflector array surface that matches well with simulations. So it's a useful tool that way. The equivalent circuit that I just showed you was, remember that we said that it only supported a current density that was X polarized. So what if we had a more complicated scatter that had X and Y components for the surface current density? Well, we can modify this technique to handle vectorial current distributions and treat it as a waveguide discontinuity problem that maintains continuity of the power density across the surface. And then the transform returns ratios end up being modified. Now we need to know the Fourier transform of the X component of the current distribution as well as the Y component of the current distribution. But otherwise it looks a lot like what we had before. So now we can analyze AES elements that have surface currents with X and Y components. For example, here is a loop, reconfigurable loop-based reflector element. You'll actually see this later in the talk that has varactors loading the 4 quadrants of the loop. And as we change the capacitance of this varactor, you can see we're changing the S11. Again, we're more interested in the S curve, the phase curve for this, and you can see that we can accurately predict the phase curve of this structure compared to HFSS, including the losses. You know, these varactors introduce losses into the reflection response, and those are accurately predicted as well. Here's another example of an AES unit cell called a dog bone that has obviously X and Y directed currents. This is a very commonly used AES element for making Huygens metasurfaces and bianisotropic surfaces. You're going to see it also again later. And you can see the equivalent circuit model also lines up very, very well with full wave simulation. And we just have these simple analytical expressions describing what the current is on the surface. A last quick example I'll show you here is a polarizing unit cell. So here's an L-shaped structure that again clearly has X and Y components of the current density. And this is useful as a polarizer because if we illuminate it with a slant polarization at 45 degrees, and then that decomposes the incident field into an X component and the Y component. And if we adjust the dimensions of this L shape properly, it becomes a linear to circular polarizer. We haven't shown the circular polarized response here. We're just looking at the S11 and S21 of this structure, but you can see again, it's matching very well with full wave techniques. So in closing, I think these equivalent circuit models are very handy because they're fast and they do give us some insight because they force the designer to think about what's the current distribution going to look like on this atom that I'm designing. And that's both good and bad. It's good because we should be thinking about these things. It's bad in that you need to form somewhat realistic expressions for these current distributions for this technique to work. So if you're inexperienced, that might be a little bit harder to do. So that inspires the next part of the talk where we're going to try to address this inverse design problem I indicated at the beginning of the talk more directly. So our approach here is actually to use machine learning for this. And that's not because everyone's doing machine learning these days, but because I honestly feel that has something to offer here. We've seen that machine learning has been very useful as a material discovery platform in other fields. Like there's this open quantum material database that's used machine learning to devise new quantum materials, and the same thing in the pharmaceutical industry. And metasurfaces are basically 2D versions of metamaterials, right? So they're materials too. So can we apply material informatic techniques to metamaterials? And the goal is not to really turn metasurface design into a black box where you push a button and we all become monkeys, but really leverage what machine learning can offer here to explore the design space more efficiently than perhaps a human designer could. And then we can look at what machine learning came up with and maybe learn ourselves a bit more about the physics of the problem. So what we'd like to do is I'd like to take all these simulations that we've run over the years and collect this into a material database, and we've done this now, and then mine this database. And once you have a good representation for what's going on in terms of the material parameters, then we can actually ask this machine learning algorithm, hey, I would like this specific, here I'm using susceptibilities, I would like this specific electric and magnetic susceptibility response, tensorial response, synthesize it. And hopefully this leads to new AES designs and characteristics. So this is an interesting problem because the forward problem is I go into HFSS or whatever, I draw my scatter, I run a simulation, and then I get the macroscopic properties. And this is called a many-to-one mapping, right? Because there are many different things that I could draw in HFSS, and I get one thing out, the EM properties. So I could use simulations for that, but I can also use machine learning for this. There are what are called surrogate models that try to learn from the results of the full wave simulation, so that when you present it with some structure that you want to simulate, the neural network tries to predict what the response is instead of the simulator. So that's a surrogate model. And that can be useful because surrogate models are faster than full wave simulators, but you need to train them first. The other way is this is what we want to do. This is inverse design. I say, I want these susceptibilities. Give me a physical unit cell that provides that. The problem is that this is a one-to-many problem. I've given you a specific set of macroscopic properties that I want, and there could be an infinite number of physical unit cells that give you the exact same response, right? And so a neural network is not designed to be a one-to-many system, right? It's supposed to have an output, a single output for a certain input that is being given. So this complicates things. Still, you can do ad hoc searches of the solutions that a machine learning algorithm can give you, or take a more systematic approach to incorporating machine learning to address this problem. And that's what we're going to talk about in this talk. So the philosophy of the approach is to replace this tedious process that we show on top with a more streamlined one. Normally, a designer would have to decide, how many layers do I want? What are the scatter shapes going to be? What are their dimensions going to be? And once I've decided all that, I simulate that, see if I've reached my goal. If not, then time to burn the midnight oil and then fire up some more simulations. So it's time consuming, resource demanding, and requires some experience for you to be able to adjust these parameters as you go, right? So the proposed approach is really to try to explore the design space more efficiently, more intelligently, exploit it, and at the same time trying to make use of surrogate models to speed this whole process up. So it should be more explorative and automated. It just has this cost, this asterisk, which is the one-time data generation cost to train the network. That's no easy task. First of all, these meta surfaces are very thin, and we generally use multi-layer surfaces for our designs to get the bianisotropy that we want. So you need a lot of data. And the nature of the design space complicates things because, first of all, the design space is very high dimensional, right? You have all these different scatters, all these dimensions that you could change. So there's a lot of things that you can tweak. The design space is also categorical, right? I might say, I've got this database of cross-based atoms. Maybe I have these ring-based atoms, these patch-like atoms, maybe these complementary structures, disc-shaped atoms. Those are all categories of scatter shapes. And our optimum solution might be none of these, right? It might lie in the space between, but the network was trained on something that was categorical. Of course, if we look at the loss function that we're trying to maximize or minimize here, this is varied landscape of maxima and minima that makes finding the global solution problematic, and our initial design space might even be incomplete. So this really makes for a tough go for optimization. Still, our first approach that I'll present here is to try to accelerate this process using a surrogate model. So that's to accelerate the calculation of the generalized scattering matrix. So here I show you a 3-layer metasurface or AES unit cell, which in this case is made up of these 3 different metal shapes separated by dielectrics. And that's represented somehow. And we know the frequency that we want to analyze this. And this surrogate model tries to spit out the amplitude and phase of the fundamental components of the GSM of this unit cell. Okay. So we try to train this deep neural network to do so. The idea being that if we can train the neural network to do this accurately, then this can replace the full wave simulator. So we train this surrogate model with a variety of what I call primitives. And we used 7 of them here. And this is based on our own experience. We find that these atom shapes work very well for solving a variety of AES problems. And so essentially we're curating the training data to try to help our neural network along here. And what we do is we will then take these primitives and form them into multi-layer surfaces that you see here. This is a 3-layer version, just by cascading the GSMs of multiple primitives together. And this also provides a lot of efficiency. So our resulting solution space has designs that are, the scatter is categorical because we started with only these 7 different classes of scatter, but the scatter dimensions themselves, which you see parameterized in the picture here, they're all variable, continuously variable. We also have the substrates to deal with because they have varying parameters and thicknesses. And of course, there's a number of layers that we use to make our stack as a variable too. So we encode all of this into an input variable that's fed into our surrogate model. I won't spend too much time about that. And then we use a more typical optimizer to try to check our unit cell, propose a unit cell, evaluate it using these rapid surrogate models, see if we've got the surface properties that we want in order to converge on the cell that's going to do the job for us. Okay, so the PSO basically updates the representation of the unit cell that's producing these parameters, and we use the surrogate model to see if we're doing well. And if this norm is small enough, then we say that we've converged and we've got the unit cell that we're looking for. So now I'm going to combine the micro step and the macro step together and show you what we can do. So this is both methods, that optimization method and this machine learning method coming together to synthesize a multi-beam AES. It's 15 wavelengths long, operating in the X-band, and it's supposed to take a line source that's very, very close to the metasurface, and from it create 2 beams, one at -10 degrees, one at 20 degrees. This is a 2D problem. So imagine that this surface that you see here is just infinitely repeated in the X direction. And we also have some side lobe level constraints. So you can see all this in the picture here. The magenta line is showing the side lobe level constraint. So this is the do not exceed line. These asterisks show where the main beams are supposed to be. And the blue curve shows what the optimizer produced. Remember, the optimizer is using a homogenized description of these surface parameters, whereas the red curve is an actual HFSS simulation of the actual atoms that the machine learning algorithm suggested as a function of position to create this response. And you can see a cross-section of the surface here. It's a 3-layer surface, and you can see it's just chosen this specific choice of atom designs to realize the surface parameters as they vary in the Y direction. And it works pretty good. We have 2 beams. These curves aren't exactly on top of each other, but these differences are somewhat expected because we're using a homogenized impedance model in the optimizer. And yet in our actual model, we have a lot of feature and structure to the actual metallic atoms, right? So we would expect that the mutual coupling situation between those 2 different situations is quite different. Here's another example where we actually take 2 line sources and try to collimate them into a single beam, so that the line sources are also quite close to the metasurface. The main beam is 45 degrees away. We stipulated that there should be some nulls in the pattern, mainly in the backward direction, so it shouldn't backscatter at all. And we also placed some side lobe level constraints that are a little bit easier to visualize on the graph here. So you can see it's also succeeded in producing that single beam from a very uncollimated source or pair of sources. And you can see this interesting arrangement of unit cells that's come up with to do that. So we're very excited about this work, and we just got the prototype for this in the lab today. So we're hoping to measure it and add one more curve to these plots here and see if the experimental demonstrator works. So the last part of the machine learning part I will talk about is a more generative approach to these cells. This approach that I showed you here was basically stuck suggesting atoms that are made up of these 7 primitives, right? There's no real generation aside from the fact that it specifies exactly the dimensions of these structures and where they're supposed to go. But we would like to invent new metasurface geometries, right? So we need a generative model for that. Maybe you guys have heard of GANs. That's one example of a generative adversarial network, but we're actually using what's called an autoencoder, a variational autoencoder for this. And autoencoders are useful because they take a high dimensional variable and they can compress them down into a low dimensional latent space. And that's useful for optimization, right? I don't want to optimize over this massive high dimensional space. I'd much rather optimize over a smaller dimensional space. But we use a special autoencoder called the Variational Autoencoder, or beta VAE, which allows us to become much more statistical. So it actually tries to model the PDF of the input in addition to the input itself. And it tries to predict the mean and standard deviation of that PDF, assuming that it's normally distributed. And that's useful because now it allows us to draw samples from this distribution, random numbers, right? And then feed that to the decoder, which then can now invent new geometries that didn't exist in our original training space, right? So this is a very interesting machine learning generative algorithm. It has a loss function that comprises what we call a reconstruction loss and a KL, Kullback-Leibler loss, divergence loss. This first term is to minimize the reconstruction loss between X and X hat, right? Like if I feed in a representation of unit cell, I expect to get that back out. So that should be accurate. Whereas this KL loss is really designed to make sure that the latent space is regularized in such a way that it's close to a normal distribution with zero mean and a standard deviation of 1 that you see here. So then to put it all together, we represent our AES unit cell, we encode it into this latent space, and then we draw a sample of that latent space and try to predict what the S parameters are at a particular frequency. And once we've got the S parameters that we want, then we can feed that back into the decoder to get whatever our structure is supposed to be. So that's done by training this VAE with actually the same primitives that you saw earlier as starters, basically, to help get it started with this. We use a 2 and 3 layer structures, again, just using some standard Rogers substrates to populate the database. Our training set's about 10,000 samples of these various primitives that you see here cascaded together to form 2 or 3 layer surfaces. And we also use PSO for this step. We basically try to realize certain S parameters from this AES. And then if we're not there yet, then we take a loop through the optimizer and we try to update this latent variable, predict what the S parameters are supposed to be. And if it's converged, then we're done, decode it and get the surface, the atom design. And if not, then go around once again. So what we hope to do is get brand new atom designs that you see here that did not exist in the training space at all. So we hope to get these weird and wonderful shapes. So here's a couple of examples. We use masks to define in terms of the magnitude response here, where we want, for example, the TE transmission coefficient to lie between. So we wanted basically the S21 for the TE response to lie between the orange and the green line. And you can see that our optimizer has done a fairly good job at doing that. And this is the design it came up with. And you might say, well, that doesn't look all that exciting. It looks like something that was in the input space, but it actually wasn't, because the dimensions of this Jerusalem cross or pair of crosses you see here wasn't actually in the training data. This is a polarizer that's designed to take an incident linearly polarized wave and turn it into CP. So in terms of masks, we say that, in a certain frequency interval, we don't want the insertion loss to be too large between the TE and TM components. And we want the phase difference to be 90 degrees, right, for CP. And you can see that it's come up with this design. And when we look at the axial ratio of this polarizer, it's pretty good over a pretty wide frequency range, 20 to 30 gigahertz, not bad. Pretty good cross-pole characteristics. And again, this design, while seemingly unremarkable, wasn't in the input space. But we tried to push this a bit harder and do a bit more of an explorative-based design and force it to invent new atom designs. So we gave it this set of masks for the TE and TM transmission coefficients, and that came up with this 2-layer metasurface that looks like some sort of interpolation of the Jerusalem cross in the patch, right? So it's very interesting to see the algorithm doing this more generation of these new designs. And I think this is very exciting. So I think it's an exciting time to be exploring machine learning or involving them in this step, given the advent of the 3 V's that everyone talks about in machine learning: volume, velocity, and variety of data. So I think this is just the beginning, and certainly the approach that I've shown you here is really just one possible way to solve the problem. Okay, I know we're getting close to the end here. I would just like to show you some experimental work just to show you it's not all completely theoretical. My group does a lot of collaboration with aerospace companies. I thought it'd be useful for you to see some space applications. So in the space applications, this antenna tends to rule a lot. And so there's been a lot of work over the years to try to get AES designs that replace these reflectors. But in my opinion, we're only going to succeed with that if we provide solutions that do more than what this thing does, right? Because this thing it's reliable, it's broadband, it works, it got flight heritage. Not really a whole lot wrong with it. So if you're going to replace it, you're going to have to do something much better. And maybe we can make it reconfigurable, including electronically reconfigurable. Maybe we can program the frequency dispersion of the surface so it behaves differently at one frequency than another, right? Satellite applications are dual band. I can't make a dish behave differently at one frequency than another, but I can make an AES do that. Same thing with polarization, right? A dish is not polarization selective, but I can make AES as polarization selective. So I'll show you just a few examples here of how we can try to bring some of this to the stage. Electronic tunability has certainly fascinated people for a long time. That was a lot of interest in spatially fed arrays, whether they're reflect arrays or transmit arrays. On the right-hand side here, I'll just show you briefly how you can do that. You could just integrate active devices like varactor diodes into the scatterer itself. And this is a very old work now, but more recent work that we've done in our group has tried to make this dual band to realize a KU band ground station for nanosats. So you recognize this unit cell. It's the one that we looked at with the equivalent circuit model with the 4 varactors. It's quite useful for this purpose. And in fact, we can put 2 of them together, different sizes, to cover the uplink and the downlink. And it turns out it's better to separate them like what you see here than to put them on top of each other, like one ring within the other, just because there's a lot more mutual coupling between them if you do that, just because they share the magnetic flux density together. We've also placed these elements on a triangular grid. So all these large rings end up on the triangular grid. All these small rings end up on another triangular grid that's offset from the other one. And this is really just to save the number of elements in the array, because for a given scan angle, a triangular array will do it, triangular grid will do it with fewer elements. So unit cell operates in the KU band. So the downlink is at in and around 11.2 gigahertz. You can see that we've got a reasonably looking S curve from the device here. And then the uplink is at 14 gigahertz. Also reasonable looking S curve. Some losses. This is the price to pay when we use semiconductor-based reconfigurable unit cells, but we gave it a go anyway. You can see a small sample of the reflector array fabricated here on a 4-layer board. Half of it's for the RF part and half of it's for the DC electronics. And this is that sample on the range just being tested with our near field scanner. And it works pretty well in both bands. It's producing beams over roughly a minus 30 to 30 degree range in front of the reflector array over a reasonable bandwidth. So we were pretty happy with this. You don't see the beams at the center just because there's too much feed blockage in this particular setup for us to measure it at broadside. That polarization problem is also a very challenging problem. Actually, the frequency polarization problem is a major problem of interest these days for satellite manufacturers. What you see here is a typical high throughput satellite manufactured by MDA here in Canada. And these satellites create what's called a 4-color multi-beam pattern on the ground. And a color is a frequency polarization permutation. So we have, let's say, a frequency F1 and F2, and a polarization P1 and P2, which are typically LHCP and RHCP, and you permute them to get the 4 colors. The problem is that it turns out that you can't actually overlap these spots as closely as we would like to maximize capacity without using an enormously large reflector. And so what what a lot of people resorted to doing is actually using 4 smaller reflectors, each of which slightly offset from each other to overlap the beams as you see them here. And that's really a lot of launch mass and volume. We'd really like to have just one reflector do this, right? But what would you need? You would need a reflector that responds differently to F1 and F2, and you'd need a reflector that can respond differently from P1 and P2. But that's exactly what AESs do, right? So if we can solve that problem, then we can reduce the number of reflectors by potentially a factor of 4. So one way that we thought about doing this is to cascade a polarizer AES with a reflector AES. The idea being that the polarizer's job is to convert CP to linear polarization, and then you can use a highly anisotropic reflector array to handle the horizontal and vertical polarizations, collimate it, and then one more pass through the polarizer on reflect, and you produce these 2 circularly polarized beams. Now you just need to do this over 2 bands. So we devised a dual band polarizer that's shown here. It's a 3-layer AES that takes RHCP and LHCP and converts them to linear polarization. But the interesting thing is that in one band at 20 gigahertz, it turns RHCP into, let's say, X, LHCP into Y. But in the other band, it does it the other way around, RHCP to Y, LHCP to X. And that's actually an important requirement for these 4 color systems. Below here is a reflector array arrangement that's also dual band. And when you put them together, then you can produce all 4 colors here. So this is the reflector array on the range. This is a space qualified feed from our partner. And we can see that this array was quite successful in producing 4 beams under 4 different beams for 4 different illumination conditions, right? LHCP, RHCP, and also F1 and F2. So you can see that these beams are all pointed in the directions more or less corresponding to the table that we wanted there. And sort of proving the concept that a reflector array engineered in this manner might one day replace that 4 reflector system. The last example and last couple of slides here, I'll just show you an interesting AES for doing extreme angle refraction. This is a bi-anisotropic unit cell design that is realized using a 3-layer AES design. And this is also for a ground station application that we're working on, that we want to try to achieve horizon-to-horizon scanning on the ground, which is pretty extreme angles, right? So we would like to be able to use AESs for this purpose. So you can actually analytically determine if you want to take a plane wave and redirect it to an extreme angle, or any angle for that matter. You can actually determine the variation in surface parameters analytically from the surface. But then the problem is that once you realize those parameters and you put the AES together like this, what we found is that when you illuminated it with a normally incident field, it actually didn't do a very, very good job. Here we tried to do a 0 to 80 degree refraction example. And actually 28% of our power is reflected. You can see this big standing wave on the left-hand side of the surface. And only actually 55% of the incident power was directed in the correct direction, 80 degrees. And you can see there's these distorted wave fronts on the right-hand side of the surface. And the problem is mutual coupling, right? We have these unit cells were designed assuming they were surrounded by identical cells, but when you look at the actual surface, they're clearly not identical, right? And you could optimize, you could use that optimizer I discussed earlier to handle this, but maybe there's a simple solution. And one very maybe obvious solution is to introduce baffles between the unit cells to limit the coupling. And for TM polarization, those baffles can actually be PEC walls between each of the unit cells. For TE, you would need perfect magnetic conductors. That's obviously a bit more challenging, but we'll focus on the TM case here. So after introducing these baffles in the metasurface that you see here, now this metasurface is doing its job, right? It's much cleaner plot on the bottom that you see on the top. And you can physically realize this using vias. You need a lot of them, but it was perfectly doable with sort of standard commercial processes. And a simulation with vias shows that it works pretty much just as good. You know, only 21% of the, or 97% of the power was directed as expected, but there are some losses. These baffles tend to exacerbate ohmic losses in the dog bone structure. So total efficiency was around 77%. This is a sample shown here. You can see it's on the range. We've got this lens to collimate the incident wave into a plane wave, and you can see it's sort of doing its job, refracting to 70 degrees. That's the -1 mode of this metasurface, and you can see it's being directed in the correct direction. So many different ways to skin the cat, right, when you're dealing with this mutual coupling problem. So that is it. I hope I know it was a bit of I'm going a bit over here. I hope it was successful in showing you kind of all stages of the design process, spanning the macroscopic and microscopic levels, as well as the demonstration level for a few interesting applications. So I will stop here. Certainly, if you have questions, feel free to put them in the chat, as they said, or send me an email. I'm happy to continue the conversation with you later as well. Thanks very much for your time.
Thank you so much, Professor. That was really interesting talk. So now we accept the question. Please, if you have any question, you can put it in the chat box, or you can just raise your hand and unmute yourself. Of course, it's, I think, a bit late in Toronto, but
oh, don't worry about that. But you guys might be getting hungry for dinner, so yeah. Thanks for your comment, Ali Reza.
So I actually have one question. Maybe I think the audience are a little bit shy. So I think it was slide 41, which you were talking about. Yeah. So well, I actually have two questions here. The first thing is that you said I require experience from realistic expression for the current distribution. So for each cell that you have, the current distribution is just not realistic. Is that what you mean here?
Okay, so so for each of these cells that I analyzed here, I proposed a current distribution, right? So for example, for these dog bones that we just saw a moment ago, if you're designing with these dog bones, then you can't form the equivalent circuit model unless you know the current distribution, because you need its Fourier transform to get the turns ratio. So step one is to identify the current distribution. So to do that, you need to know a little bit about what would happen to this dog bone structure if it were illuminated with a plane wave, for example. And what we might expect is, just from antenna theory, is some sort of current maximum in the middle that tapers off towards the edges, and then sort of conservation of current at this junction, right, like KCL to handle. So overall, if this dog bone was, let's say its effective length was close to half a wavelength, then you would expect that you have some sort of half wave cosine going from the middle all the way out to the edges, right? But you need to be able to suggest that current distribution, and that's what's done here. That this is basically an equation, potentially an equation for that half wave cosinusoidal variation, depending on how much reflection we expect off the ends of this dog bone, which it's basically an open circuit. But you need to be able to form these expressions as part of step one. And so that's what I mean by informing the equivalent circuit model. If you have no knowledge of the current distribution, then the ECM isn't going to be very useful to you. Or if you do a very bad job in suggesting the current distribution, it won't be very accurate.
Do you use sort of like a reciprocity theorem? Like, let's say, just eliminating this, just see the induced current, and then like from there, you guess the current distribution, or just like it's merely based on intuition? Like,
you could, yeah. Practically, that's what we end up doing is, that's what an experienced designer how they would approach this problem, right? Is they would have seen in simulations before that when I illuminate a dog bone in this way, this is the current distribution that comes up with. But the hope is that you don't have to rely on the full wave simulator to give you the current distribution, because if you did, then you might as well just use that, right? So the idea is to suggest the current distribution that's close enough to what actually happens to give you first order accuracy in the response for design purposes, and then refine later, right? So the fidelity of the model is not intended to be super high, but good enough for initial design purposes.
I see.
Yeah.
So we have a question in the chat box. Surush is asking for the K-band antenna. How robust is the beam and the side lobe level against 5 to 10% PCB thickness variation?
Oh, okay. So I assume by Ka band antenna, we're talking about that multi-beam antenna that I showed at the end. Is that correct, Suraj?
So if you want,
Yes.
you can unmute yourself.
Okay. So that's this one here. So you're wondering how robust the beam is against 5 to 10% PCB thickness variation. So I assume you mean the thickness of these individual components, the polarizer and the reflector rate. It's probably, we didn't, so I'll be honest, we didn't study the impact of PCB thickness on the result. But these designs are not extremely sensitive to the geometric parameters of the structure. So I would suggest that there's some wiggle room, given that these are quasi-resonant structures, in terms of dealing with different substrate thicknesses. Like I can tell you that these substrates flex and bend, and it's actually quite difficult for us to keep them perfectly flat. And yet the structure still worked pretty well. I hope that answers the question. There's another question. In multi-layer designs, are the coupling effects of the elements considerable in typical equivalent circuit models, especially for thin substrates? Okay, very good question. So yes, of course, we want to capture coupling effects. If we go back to the equivalent circuit model, let's show you a picture of that again, just to refresh ourselves here. Maybe I'll go to the driven one. So it's true, when you have, let's say, two metal layers close to each other, there can be coupling between them. And that coupling can manifest itself as low order coupling or high order coupling. So by high order coupling, I mean the evanescent Floquet modes talking to each other, right? So the equivalent circuit model, and by low order coupling, I mean that even if the cells are reasonably distant from each other, you still have the fundamental mode causing interaction between the two layers. So the equivalent circuit model definitely works well for the fundamental mode coupling, because you can predict it like in the same manner as I showed here. In principle, the equivalent circuit model can be adapted to also capture the higher order coupling, because you can see here that I could excite this port and I actually could see what comes out all of the other ports here. And there's many of them, right? This goes on ideally forever. So there's many ports, and I could see how much of the higher order modes are being excited, the evanescent modes are being excited, and then couple that to another equivalent circuit model for the next stage. The problem is that we don't know what the current distribution necessarily looks like for these scatters when they're illuminated with the higher order modes. So like just a moment ago, Kazim was asking about the current distribution on the atoms, and we can see that we have to suggest something, and that's for a fundamental mode illuminating that atom. If it's being illuminated by a higher order mode, it's probably a lot harder to guess what the current distribution may be. So that's a potential gotcha with using this equivalent circuit model for really, really thin equivalent circuit models, but in principle, it should work. Yeah. Good question.
Thank you so much, Professor. I think, let's see if we have one last question.
There is one more question.
Okay. Yeah, how much effort goes into training these machine learning models? How accurately would it work for relatively complex unit cell geometries outside of the patch and Jerusalem cross? Okay, so yes, there is some upfront effort in training these machine learning models. Typically, we need around, like in the one example I showed you, there was 10,000 samples that we used to train the model. So that's a lot of simulations. And we actually have found very clever ways to accelerate our simulations to make that 10,000 simulation doable in a reasonable time. But it actually does a pretty good job with complex unit cell geometries. I showed you how it's very good at interpolating, right? Like I showed you this unit cell where it was put in a more generative mode, and it came up with this interesting scatter shape that's neither a Jerusalem cross nor a patch. So this is promising because this design lies in the space between primitives that it was trained on. But what these networks are not good at doing is extrapolating, right? So if we want to come up with some radically new, or what you're calling a relatively complex unit cell geometry that lies well outside of the training interval, they're not so good for that. And that would require just more augmented training as you go, as you generate these new shapes, or other approaches. And so we're looking into that using GANs now, actually, to try to address this problem, to deal with more complex geometries. But I think all things considered, considering we have a 3-layer unit cell with these many different primitives that can realize a huge range of surface parameters, it's already doing pretty well. So I'm optimistic, I guess, despite the large training cost. I see Ashwin has got us. Ashwin, you're not in California.
No, I'm not in California, Sean. How are you doing? Great talk. It's my pleasure. Really, I learned a lot. Fantastic talk, as usual. I just have a very quick question. Do you mind going to slide 51?
Sure.
Right here. So you mentioned that using the homogenized model versus using the full structured model, that you would expect that the structured model better achieves the criteria that you've set out here, is it basically because you have more degrees of freedom available to you in designing that structure and in compensating for things like the mutual coupling, which is lost in the homogenized model? Is that right?
What I was trying to say is that when you look at these two curves, they don't seem to match, right? And that's because of differences in the way mutual coupling is handled between the homogenized model and the actual physical model. Because in the homogenized model, we just have impedance sheets next to each other, right?
Yeah.
And while the mutual coupling is handled, it's just mutual coupling between uniform impedance sheets. Whereas obviously, when you have this physical structure, the mutual coupling is very likely different from what was happening in the 3 impedance sheet model. So that's
to explain the difference. Yeah.
Yeah.
I fully understand that. Thanks for that. I'm more about achieving the side lobe constraints, though. Is there a good reason why it's more difficult to achieve the side lobe constraints using the homogenized model than with the full structured model?
So I thought it doesn't always work this way. Sometimes the physical model does worse than, actually the simulated model is the one is the HFSS model.
Okay.
And the red curve is the homogenized model. So you can see that the side lobes are actually worse, and we're exceeding the constraints. And that's part of that is because in our machine learning database, we actually only illuminate the unit cells at normal incidence.
Right, yeah.
And then obviously we don't have that here with a cylindrical line source.
Mm-hmm.
So that wasn't even accounted for in the design. So so if we had accounted for that, then we would probably get closer correspondence between the two curves, despite even still the difference in mutual coupling mechanisms between the two.
Okay, perfect. Thanks very much.
Yeah, thanks for coming, Ashwin.
Thank you so much, Professor. Thank you so much all for attending this talk. We shall conclude that right now, and hope you all enjoyed. Thank you again so much for attending and inviting for lecture.
Thank you, everyone, for coming.
Have a good night.
Thank you so much, Professor.
You're welcome.
Thank you.
Best of luck with your chapter's activities. Thanks.
Yes, so much. Hope to see you in person.
Thank you so much.
I look forward to
Hope
it.
to see you in person. Yeah. Thank you.